All right, so we're going to conclude topic 6.2.3, so we'll label this in order. 6.2.3, and that's a point. And so this is going to be about, so far we've learned that there's alpha, beta, and gamma particles that are emitted from the nucleus of an atom, hence nuclear physics. And we've learned the properties of them. Remember, alpha ionizes the most particles of gas, and beta the next, and then gamma the least. And penetration-wise, gamma, many centimeters of lead, beta, a couple centimeters of like aluminum, for instance, not centimeters, sorry, millimeters. And then alpha, so big, helium nuclei, remember, can even a good sturdy clothing can block it. So now we're going to learn where these come from and look at the equations that they create when they do decay out of an atom. So let's sort of remind ourselves. We have helium nucleus is the alpha particle, and then the electron is the beta particle, and then the gamma particle is the symbol is that, and so I'm just going to put it twice. So this is alpha, beta, and gamma. And so we're going to go to the next page, and periodic table. So let's just see if I can sneak these in here and put these down underneath here. So let's just pick some elements here. And how about, oh gosh, I can't really see. There we go. So we'll pick thorium for our first one. So thorium, and that's atomic number 90. And unfortunately, the periodic table that I picked doesn't have the. So you know what? I'm just going to refer back to the to one on the bigger screen. There we go. And okay, so thorium, atomic number 90, and let me just pause. Okay, so we're back again. I got thorium atomic number 90, and I need to I had to look up, get a periodic table that gave me all the masses and everything. And so we have atomic number 90, atomic mass of 232. And so let's think about this. So what happens if thorium through the radioactive processes going on inside the radioactive, it decays and it gives off a alpha particle. So here is an alpha particle, and so there's the particle ejected from the nucleus of the atom. So let's just take a look at what would happen. So what would be the new daughter material that comes from this? So this is the parent material, and then this would be the daughter material. And so 90 minus 2 would be the new element would have atomic number of 88, and the new atomic mass would be 228. So then we'd use our periodic table and look that up for the atomic number of 88. And if we look on our periodic table, we find that is radium. So we'd put radium in there. And so there's how alpha decay. And so you can have a whole chain of these reactions taking place. So now I'm going to use the radium here to show you a beta decay. So I'm going to go to the next page, and I'll put radium on there. And that was, 228.88. So 228.88. Now, one thing to note here, you may look on the periodic table and find that the atomic mass is different than the mass on the periodic table. For instance, the atomic mass on the periodic table is 226, and this has a mass of 228. So this is just an isotope. And if you want to talk about it specifically, I guess you could call it a nuclide. Remember, a nuclide is a specific number of protons and neutrons, but this is an isotope of radium. So now let's let radium undergo a beta decay. So a beta particle, as you know, has a -1, and and we remember that beta particles come from the neutron in the atom, and so let's just sort of look at that. So that neutron decays into an electron and a proton. So what's going to happen if you think about this, all the neutrons and protons are up here, so what's going to happen to one of those neutrons? Well, it's going to become a proton. It doesn't exit, only the electron is radiated. So the proton number now goes up by 1. So our new atomic number would be 89. And then remember that the neutrons and protons contribute to the mass of the atom. The electrons really don't, so the atomic mass would stay the same. So it would be 228 still. And so we just went up the periodic table by 1, and so here we have an electron with a -1 charge. That wrong place for that. That's the mass, sorry. That -1 charge and 0 mass. And so if you put all this together, so you do 88 minus a -1, so let's just see how I got that. 88 minus a -1 yields 89, and that's where I got that atomic number from. Remember, that's the atomic number. And then 228 minus 0 yields 228. So that's how I got the 228 over here. So now I look on the periodic table, and that's actinium. Actinium. So now we have and you could use any element that could undergo this. One thing that you're going to see in your book is that they'll give you plus an antineutrino, and don't really worry yourself over that right now. I'll introduce you to that in a couple chapters, but it also yields an antineutrino, and so here I'll just sort of add it in here. So plus, it's a V looking thing with a bar over it, and it's 0 mass, 0 charge. And V sub E, they're an antineutrino, okay? And then a neutrino doesn't have the bar over it. So we'll consider that later. Okay, then the last one is really easy. Let's just take the actinium. Remember, I could use any element on the periodic table and undergo this process. However, hydrogen can't give off an alpha particle because it's smaller than it. So, so now we have actinium, and I'm going to go 89 and 228. And remember now that the alpha particle, going back a couple slides if you want, is massless and chargeless. So yields, it's going to give off, I said alpha, I meant gamma. The gamma particle is going to be given off here, so the gamma particle, 0 mass, 0 charge. And so if you look at this, you have, 228 and 89. And so it yields actinium again. Now, you might wonder what's going on here. Well, what happened was that the nucleus of the actinium atom had to absorb some energy from somewhere, and it absorbed it, and then it re-emitted it. Remember how we did how we got the Bohr model of the atom, how it emitted particles? Well, that's exactly what you're seeing there. The Bohr model, it absorbed incoming radiation, caused an electron to jump up a level, and then when the electron dropped back down, it gave off a photon. Well, the same thing is sort of happening here in the nucleus of the atom as well. The nucleus is absorbing some energy, and then it is giving off a massless, chargeless gamma particle. All right, let's wrap this up. So the two key things here. You've got there's the law of radioactive decay that I want you to know about on page 377. Page 377, law of radioactive decay. Let's see if I can radioactive decay. I'm messing up big time. There we go. And that is just that the number of nuclei that will decay per second, in other words, a rate of decay, so nuclei per second decaying, is proportional to the number of atoms present that have not yet decayed. So make sure you look up that. And then on the same page, the half-life definition. And so half-life, and a lot of people really know this, but I want you to know the definition that they give, because they always sort of do that. They say define half-life. So half-life, think about if you have 100 nuclei, and let's say that it takes them 1 day to decay, or for half of them to decay, then that's its half-life. And so after 1 day, the number of nuclei present would have decreased by a factor of 2. And then after 2 days, the number of nuclei now present would have decreased by a factor of 2. So just I'm going to read it to you. It says there exists an interval of time called the half-life, such that after each half-life, the number of nuclei that have not yet decayed is reduced by a factor of 2. So please make sure you look at those on page 377. And last thing that you want to just be aware of is graphs and how you can get information from it. And so there's some graphs on page 378, which I'm most likely going to go over with you in class. But they plot the nuclei and time, and then if you start off with say some amount and it decays down exponentially, and then the other would go in this direction. So the number of daughter material. So we'll go over that more in class. And so anyway, I'm going to wrap this up with that and let you sort of absorb that. And so I hope that you can watch all 3 of these videos and we can have a good productive day tomorrow. Our first day back from winter ice break. Okay? All right. See you tomorrow. Bye.